Okay, we've got a long answer problem here, and it has to do with sulfur. So we've got sulfur in some of its compounds. This is actually going to be 8 problems. So I've got the first 4 here, then we'll do the next 4 after that. So first, write the balanced equation for the combustion of S8 to form SO2 gas. So this is pretty easy. We've got S8. And so combustion, whenever we hear the word combustion, we know that we are reacting with O2, right? So let's put solid there, and we'll put gas there. And so if we are combusting sulfur with oxygen, we're going to get SO2, or it's telling us we're going to get SO2 gas. So that's the equation. Now we got to balance it. Again, pretty easy. We've got 8 sulfurs on the left, only 1 on the right. So we got to put an 8 right there. And then now we have 16 oxygens on the right there. So we've got to have 16 oxygens on the left. So we've got 1, 8, 8. That's the ratio there. That is the balanced equation. So this one's good to go. Now, calculate the volume of O2 gas measured at 1 atmosphere and 298 K that is required to completely combust a 500 gram sample of pure S8. So, a little bit of stoichiometry here. Now, we've got 500 grams of S8. So we're going to want to convert that to moles. So I've got the molar mass here. We've got 1 mole over 256.5 grams. 1 mole over 256.5 grams. So now we've converted that into a number of moles of S8. Now we need the stoichiometric ratio because we want to learn something about O2, and we've got 8 moles of O2, right? If we this is S8. This is 1 mole S8, and this is grams of S8. And so we're going to multiply that by 8 moles of O2 over 1 mole of S8, right? Because we want moles of S8 to cancel like that, right? It's an 8-to-1 ratio. So if we do all that and we plug that into our calculator, we get 15.60 moles of O2. So that's the number of moles of oxygen we're going to need in order to completely combust this 500 gram sample of S8. So that is that. So B is done. Now for C, a student claims that the combustion of S8 is an oxidation reduction reaction. Justify the claim. We need the oxidation numbers before and after. So let's go ahead and do that. Now this is actually also quite easy if we remember how to assign oxidation numbers. For any pure element, it's going to be 0. So we've got pure sulfur over there, that's 0. We've got pure oxygen over here, that's 0 as well. And now in the product SO2, we know that oxygen is almost always -2, right? Unless it's part of peroxides or something like that, we can count on oxygen as being -2. And there are 2 of them. So sulfur must be +4 to get this to be add up to 0 altogether. So this is a redox reaction. All right, very clearly sulfur has been oxidized, which makes sense because it's reacting with oxygen. So oxygen is an oxidizing agent. So sulfur got oxidized, and then oxygen got reduced. So we do want to be able to get these oxidation numbers. So that looks good. We got C. And then in the box, where if they provide a box, we want to draw a Lewis electron dot diagram for one valid resonance structure of SO2. So how are we going to do that? Again, the easiest way to draw resonance structures, SO2, we know sulfur is going to be the central atom. So here's sulfur, and we know that sulfur has 6 valence electrons. So let's draw them. 1, 2, 3, 4. Remember, put 1 in each coordination site before doubling up. And then let's just put 1 more up there and 1 more down there. So there's sulfur with its 6 valence electrons, just like oxygen, right? It is an analog of oxygen. And so now we've got another oxygen over here and another oxygen over here. Again, we know that these guys are going to have 6 valence electrons also. So let's do the same thing as we did for sulfur. And where we have unpaired electrons, we can draw a bond. So there's a bond there. There's a bond there. And now we can, we have more unpaired electrons on oxygen. So the easiest thing to do here is to take one of these lone pairs and split it up. So let's get rid of this lone pair and these unpaired electrons. And let's just go ahead and make 2 more bonds. Okay. So there's SO2. Now the geometry, we're going to talk about the geometry in a second, but this is a valid Lewis dot structure. If we were going to go ahead and depict the geometry, we would want to do this. Right. First, we were just figuring out how the bonding is working out. But now that we know the number of electron domains, we know that sulfur has 3 electron domains: oxygen, oxygen, lone pair. That is going to be trigonal planar. Now that's so this is probably the easiest one to do. The other valid ones would be if one of these pi bonds was to go up to this oxygen, right? If we went like this. So what would that look like? That would look like this. That would have a minus charge, and sulfur would now have a plus charge, right? So it would still be neutral overall, but oxygen would be contributing 7 electrons. That's 1 more than its valence, so a minus charge, and sulfur is contributing 5 electrons, 1, 2, 3, 4, 5, and that's 1 fewer than its typical valence of 6, so that would be a plus charge. And then, of course, we could do the same thing going the other way. 2, 3, 4, 5, 6, 1, 2, and a plus, 1, 2, 3, 4. So these would be the 3 valid resonance structures. So we wrote the equation for the combustion of S8 and balanced it, and then we figured out the volume of O2 required to combust this mass of S8. Then we assigned the oxidation numbers for that reaction, and then we drew the Lewis dot structure. So let's move on. Now, based on the diagram we just drew, so let's show that again. Right. If we do this, we know that that's trigonal planar. What is going to be the oxygen-sulfur-oxygen bond angle right there? What is the angle going to be here? Well, that's clearly going to be 120 degrees, trigonal planar, or it's going to be approximately 120 degrees. It does say approximate because it doesn't need you to memorize, right? When we replace one electron domain, if from an atom turn it into a lone pair, that does change it a little bit. But we can just say 120. Trigonal planar, it's about 120. So now SO2 can be oxidized to form SO3 according to the following equation. So we're going to react that with additional diatomic oxygen. We're going to get SO3. And here's the delta H associated with that reaction. So first of all, is the value of delta S for the reaction represented above positive or negative, and justify your answer? So we're talking about a change in entropy. So the entropy, right? Entropy has to do with the degree of dispersal of matter and energy. And so when we're looking at this kind of reaction, so these are all gaseous products. That's very important that we understand that these are gaseous products. And what we are doing is we are going from 3 moles of gaseous products to 2 moles of gaseous products, right? We have 2 moles of this and 1 mole of that for a total of 3 moles, and we're going to 2 moles over here. And so this is a reduction in entropy. This is a reduction in the dispersal of matter. We are going to fewer moles of gas, right? Gas molecules are fusing, right? SO2 and O2, right? These particles are fusing to form fewer particles of gas, and so that is entropically unfavorable, and that is going to be negative. We're talking about a negative delta S right there. So that is going to be that one. And then, so the next one is the magnitude of delta H for the reaction to form SO3 liquid, represented above, greater than, less than, or equal to the magnitude of delta H for the reaction to form SO3 gas. So we're talking about the difference between liquid and gas. And so what do we understand here? If we're going to form, if let's say we're forming the gas, and that is going to be negative 198 kilojoules per mole. What would happen if that gas was to liquefy? Would that absorb or release energy? Well, certainly it would release energy. Anytime we're going from gas to liquid or liquid to solid, that is going to release energy, right? Because the gas particles, they're far apart and they're not interacting. But in the liquid phase, they are making electrostatic interactions. And when you have particles that are not interacting and then they're interacting, those interactions release energy. The system goes to a lower energy. So the delta H is going to be even greater in magnitude. Now, be careful. The wording is a little bit different. Is the magnitude of delta H, so irrespective of sign, right? You could be tempted to say, right, so the delta H going all the way to liquid is going to be less than this in the sense that it is more negative. So that's why they specify magnitude, because we're talking about a larger negative number. So it's going to be negative greater than 198, right? Negative 200 something, 300 something, etc. And so this part is a little tricky, the exact wording of it. But all we have to understand is that if we got the gas, this is the delta H. If that was to liquefy, it would release even more energy. So it would be the total would be a delta H of an even greater negative number. So the magnitude of the number is greater. So that can be a little bit confusing, but just be very careful with the wording, right? The word magnitude is important, and then again, obviously, we're just understanding that liquefaction, right? If we're going, or condensation, I should say, that's an enthalpically favorable process that is going to release energy, no matter what the substance is. And then finally, based on the information above, how does the thermodynamic favorability of the reaction change as the temperature of the reaction system is decreased? And we want to justify this. So we've talked about enthalpy and we've talked about entropy, and now we're talking about we want to talk about thermodynamic favorability overall. So clearly we are talking about Gibbs free energy, right? We've got delta G equals delta H minus T delta S. So what did we just say about each of these parameters? For delta S, is that positive or negative? So that's negative, right? And then delta H, we know also is negative. And thermodynamic favorability, right? Favorable means if it's thermodynamically favorable, it's spontaneous, which means a negative delta G, right? So this is a situation where we have a negative delta H and a negative delta S. A negative minus a negative could be negative or positive, right? And so that sounds maybe a little confusing, but just remember, if we have a big negative number, let's just say negative 10, and then we're doing minus negative 2, well, that will be negative 8. So we're still plenty negative, and that will be thermodynamically favorable. But if we have negative 10 minus negative 20, that would be positive 10. So it depends on how big this term is, right? They're both negative, but if this term is very large, then the negative delta H, it will be canceled out. It will be positive overall. This whole expression will be positive overall. But if T delta S is a very small term, then delta H, that negative delta H, it will remain negative overall if this is not big enough to turn that positive. And so the question is, how does the thermodynamic favorability or the spontaneity change as the temperature of the reaction system is decreased? So if the temperature decreases, if the temperature decreases, then this whole term is getting smaller and smaller, right? And if this term is getting smaller and smaller, then the whole expression is getting more and more negative, right? If you have negative 10 minus negative 5, that would be negative 5. If you have minus negative 4, negative 3, negative 2, negative 1, we're staying closer and closer to that negative 10. Right? If this, in the limit of this becoming very close to 0, we stay at roughly where that delta H negative value would be. And so what that means is that as the temperature decreases, the thermodynamic favorability increases, right? The thermodynamic favorability increases. So again, the wording is a little Funny, right? The delta G is getting more and more negative, but what that means is that the thermodynamic favorability is increasing. So we have to have all of these thermodynamic parameters understood. What do they mean? How do they correlate with, or how do positive and negative values correlate with enthalpic and entropic favorability or unfavorability? And the same going for spontaneity. And then just being very careful with the wording. What is it saying? Thermodynamic favorability, right? The temperature decreases, delta G gets more negative. That means thermodynamic favorability is increasing. So that was a really good one. We talked about VSEPR and molecular geometry. We talked about oxidation numbers. We balanced an equation. We talked about thermodynamics. This is a really good problem, synthesizing a lot of stuff here as it pertains to sulfur.